ancient objects, the remains of life, of civilizations from the past. But from how long ago? How old are they? How can we ever know? We now have the means of finding out. Age, of course, is the measure of a length of time. We can measure time by using something that changes at a known rate. If you know the rate at which a candle burns, you can use it to measure short periods of time. But scientists must use something that changes at a much slower rate than burning candles for measuring very long periods of time. The substances they use are radioactive atoms. Now, every living thing contains atoms of carbon. Most carbon atoms have an atomic weight of 12. While carbon-12 is stable, not radioactive, its isotope, carbon-14, is radioactive and unstable. Carbon-14 is formed in the high atmosphere when nitrogen atoms are bombarded by high-energy neutrons. When it decays, a carbon-14 atom shoots a high-energy electron from its nucleus and changes back into nitrogen. Both carbon-12 and 14 are absorbed by green plants in the form of carbon dioxide during photosynthesis. Animals that eat the plants also absorb both isotopes of carbon. Radioactive carbon-14 can make its presence known. Take a leaf, for instance. We know that radiation can create an image on photographic film, so we'll press leaves onto film and wait overnight. It turns out that the leaf absorbed enough carbon-14 while it was growing to take its own picture. Even so, only a very small proportion of its carbon atoms are carbon-14. For every one carbon-14 atom it contains, there are about 1 trillion carbon-12 atoms. This ratio has remained fairly constant for many thousands of years, but when a plant or animal dies, it stops absorbing both carbon-12 and carbon-14. And this ratio begins to change as the radioactive carbon atoms keep decaying to nitrogen without being replenished. Only half of them will be left after 5,700 years. And only half of that half will be left in another 5,700 years, and so on. 5,700 years is carbon-14's half-life. When we know what fraction of the original carbon-14 is left, we have an idea of how old the material is. With radiocarbon dating, we can find the age of organic materials like shells, bones, or charcoal from an Ice Age campfire. We'll test these bits of partially burnt wood to find their age. First, we bathe the wood in pure oxygen at high heat. The carbon, including carbon-14, burns off as carbon dioxide, which we bubble through several chemical baths to wash away impurities. We feed the purified carbon dioxide into a Geiger counter, which will count each time it is hit by a high-energy particle from the decay of carbon-14. A computer will help us translate the rate of decay into a proportion that compares the present ratio of carbon-14 to carbon-12 in our sample with the original ratio. The computer can plot this information on a half-life graph and then estimate the age of the wood. Our sample of wood came from a tree that died approximately 6,830 years ago. Information about how and when an area has changed can come from dating ancient life. Consider this bay, for example, the flat coastal land around it and the nearby ridges. What was it like here several thousand years ago? Can we find out? If we climb one of the ridges and look around carefully, we'll find some clues. This is a freshwater spring, but the water flows over fossils of coral, which only grows in salt water. So this region must have been under the sea at one time. But how long ago? This is what we learn from our data when we test several bits of the coral by the radiocarbon method. Every sample is at least 6,000 years old. The date suggests this land and the ridges around it were under the sea 6,000 years ago. So at some time less than about 6,000 years ago, either the land rose or the sea receded. And today, the environment is quite different here. The radiocarbon method can be used to date young rock containing carbon, as well as once living things. But it has a major disadvantage. The radiocarbon method is not useful for helping us date very old materials. After about 40,000 years, the amount of carbon-14 in a substance becomes too small to measure. To find the age of even older substances, both organic and inorganic, we can use another kind of atomic clock, but one that uses up its radioactive material over a longer period of time. This slower running clock is provided by the radioactive element potassium-40. Potassium-40 slowly decays to calcium-40 and argon-40. The rate at which potassium-40 decreases and calcium and argon increase in a substance is known. Potassium-40's half-life is 1,300,000,000 years, far longer than carbon-14's. Potassium-40 is very common in igneous rock. Using what is called the potassium-argon dating method, we can find out, for instance, how long ago a volcanic eruption took place. Hot molten lava contains potassium-40, but no argon-40 at all. The lava's radioactive clock will start when it cools and hardens into solid rock. Then the rock's potassium-40 content will begin to drop, and its argon-40 increase at a known rate. So when we test this volcanic rock for argon-40, any we find must have come from the decay of radioactive potassium. The more argon compared to potassium, the older the rock. We begin our argon hunt by crushing the rock. Then we melt the rock particles in a vacuum to release the argon gas. The argon in the apparatus will be cooled by liquid nitrogen and collected in the glass tube. Now the argon is ready for the mass spectrometer. The amount of potassium will be measured by another process. we have an argon reading. Through this method of potassium-argon dating, we find that these rocks were produced from a volcanic eruption 200,000 years ago. The potassium-argon dating method is the most frequently used atomic clock. It can also give us information indirectly about the age of organic substances. By dating volcanic rock in layers of the earth where fossils are found, we can get an idea of the age of the fossils. We can use potassium-40 to date rocks and to determine the age of organic materials whose carbon-14 is no longer measurable. The ancient history of the Earth itself is often revealed by radioactive dating methods. Under this protective tent, a drill is boring through the Earth. Drills like these bring up samples or drill cores from deep within the crust of our planet. The ages of these samples can be measured not only by using potassium-40, but also with radioactive atoms with much longer half-lives, like uranium-238. Its half-life is 4.5 billion years. We have gained information about vast geological changes using the various radio dating methods to find the ages of layers in a core. The radio dating methods that help us look into Earth's past have helped us reconstruct something of our moon's history as well. Astronauts have brought back rock samples from various regions of the moon. The rocks, dated by radioactive methods, were found to be as much as 4.5 billion years old as the Earth itself is believed to be. The moon's ancient rocks may well reflect the geology of the Earth when it was forming. Without radioactive dating, all this knowledge of the Earth's distant past would be hidden from us forever.